Hello everyone, myself Dr. Anindya Sundar. I am working as Assistant Professor in Department of Electronics and Communication Engineering in Swami Vivekananda Institute of Science and Technology, Dakshin Govindapur, Kolkata. And this is lecture number 7 of the subject Control System and Instrumentation. And the topic of this lecture is Routh-Hurwitz Stability Criterion. Now, first of all, let me tell you about the definition of stability of a system. Now, a system is said to be stable if it produces a bounded response to a bounded input. Okay. When the state initial conditions are zero, that is called zero state response. And there is another definition, that is a system is stable if the zero input response due to finite initial conditions return to zero asymptotically as time goes to infinity. That is called zero input response. Okay, that means we have applied a zero input, but due to the initial conditions, okay, your output of the system returns to zero as time goes to infinity. So these are the two definitions of stability of a linear system, and according to the waveform or the response of the output, okay, that means for a for an unstable system, okay, the response will increase without bounds and will never return to equilibrium state. For first order system, it will start increasing, and as time goes to infinity, the value the output response value should go to infinity. If it is second order or a higher order system, it starts oscillating and amplitude is increasing with respect to time, and as time goes to infinity, the value may reach to infinity. Then we can say the system is unstable. Now, to find out the stability, what we require is the transfer function of the system for a linear system. Okay, transfer function can be written in output, Laplace of output to Laplace of input. Okay, so we have two polynomial, numerator and denominator polynomial, that can be written in this particular form. Okay, and order of the system is maximum power of s, okay, in the denominator, and denominator polynomial equal to 0 is known as the characteristic equation. Okay, denominator equal to 0, and ds is known as characteristics polynomial. Okay, now the roots of the numerator polynomial are called the zeros of the system, because if we put the roots of numerator value in transfer function, what will happen? Your transfer function becomes 0. Okay, the roots of denominator polynomial are called the poles of the system. Okay, that means if we put the pole value, okay, in the transfer function, your system output becomes infinity. Okay, that's why these poles, the value of poles makes our system output equal to infinity. Transfer function value goes to infinity. That's why poles are the main factor for stability of the system. Okay, now stability of a linear time invariant system is a property of the system and is independent of its input. Okay, sorry. It can be shown that the positions of the root of the characteristic equation, that is the poles of transfer function in the complex plane, determine the stability of the system. If all the roots of the characteristic equation, that is the poles, are on the left side of the complex S plane, okay, that is all the roots have negative real parts, then the system is stable. Okay, if there is at least one root or pole on the right hand side of the S plane, then the system is unstable and the response will increase without bounds with time. If there is at least one root or pole with zero real part, that is lying on the imaginary axis, then the response will contain undamped sinusoidal oscillations, okay, or a non-decaying response. Then the system is called marginally stable system. For example, let me just show you. This is the S plane where S equal to sigma plus j omega, and we have a pole, okay, on left half of S plane. So the characteristic equation, I mean the transfer function, we can write some constant divided by S plus A. If you put S plus A equal to 0, okay, characteristic equation, then S equal to minus A. Okay. Now if you convert that transfer function a by s plus a, take Laplace inverse, the expression will be a to the power minus at. So the response is decaying, okay, exponentially decaying. So the system is stable system. Now if we have a pole on right half plane of the system, then if you take the transfer function is a by s minus a, okay. Now if you take Laplace inverse, the response will be a e to the power plus at. That means exponentially increasing. So it is not bounded output, okay, with time. So that impulse response is exponentially increasing. So it is unstable system. Now let us take the example of a complex pole. Okay, so we have complex conjugate roots. So this is the transfer function a divided by s plus a plus jb plus a star s plus a minus jb. So we have poles at minus a plus minus jb. Now if you take Laplace inverse of that particular transfer function, okay, what you will get is 2a e to the power minus 80 sin bt plus 90. Now here we can see we have a sine term, okay, but it is multiplied with an exponentially decaying function e to the power minus 80. So what we will have, the magnitude, amplitude of that signal is decreasing with respect to time. Okay, so that response is a damped sinusoidal, okay, sinusoidal signal, but it is damped because of the factor e to the power minus 80. So output response is going to decay and it will reach the steady state value. So it is called a stable system. Now if we have poles on right half plane, complex pole, so then the transfer function is a by s minus a plus jb plus a star s minus a minus jb. Now if we take Laplace inverse of that, what we see here, that the expression we have e to the power at term multiplied with sine term. Okay, e to the power at means it is exponentially increasing, so the amplitude of the signal will be increasing, okay, with respect to time. So the system becomes unstable because at t equal to infinity, the amplitude value may reach to infinity. Now, if we have complex pole on imaginary axis, that means real part equal to 0, transfer function is a divided by s plus jb plus a star s minus jb. If you take Laplace transform of that particular term, what you will get equation 2a sine beta bt plus 90. Now this is only a sine function, so it will be completely oscillatory in nature. Okay, so that is called marginally stable system. Now if we have complex pole on imaginary axis, multiple pole, double pair of roots on imaginary axis, double pair, that means a divided by s plus jb square plus a star s minus jb whole square. Now if you take Laplace transform of this transfer function, what you will get is 2a into t sin bt plus 90 degree. Now this term t is nothing but a ramp function, okay, that is multiplied with this sine factor, sinusoidal. So what will happen, its magnitude will be increasing with respect to time, okay. So your output becomes unbounded, okay. So that then it is called marginally stable. That means if we have a single pair of roots on imaginary axis, system is marginally stable. If we have double pair of roots on imaginary axis, system will be unstable. Okay. Now, what will happen if we have a pole on at origin, that is a by s, so s equal to 0. Okay. Then if you take its Laplace inverse, it will be a, so a constant. So it is called a marginally stable system. Now, if we have double root at origin, okay, that is a divided by a square term, okay, then if you take its inverse Laplace transform, you will get a into t. So t means a ramp function, so it is increasing with respect to time, okay, linearly. So at t goes to infinity, it should go to infinity value. So the system becomes unstable. So if we have a single root at origin, it is marginally stable system. If we have double root at origin, it will be unstable system. Okay. So these are the factors that we have to remember. Okay. Now this is the, if we have pole at imaginary axis, okay, it will be completely oscillatory. Okay. And if it is going away from this frequency will be lower, and if it is pole on right hand side, system will be unstable. Okay. And on left hand side, system will be stable. And as we go further away from your imaginary axis on left hand side, your response will be more faster. Okay. It reaches the steady state value faster than if it is close to imaginary axis. Okay. So now let us take some example that we have a system. Okay, this is the block diagram representation, unity feedback, negative feedback system. Okay, so we can find out its overall transfer function using the formula g by 1 plus gh. From that we can find out the characteristic equation. From that we can find out roots of the equation. Then we can plot in S plane. What we can see, all the roots of the characteristic equation or poles are on left half plane of S plane. Okay. Then we can say system is stable. Now, if we have this true, we have complex pole, so we are getting a response like underdamped response. Okay, underdamped response where we can observe in this particular case. Okay, underdamped response, and system is stable because all roots are on left half plane. Now, if we have another uh, transfer function, and we can see the characteristic equation is this one. If you solve this one using this formula g by 1 plus g, because a is equal to 1 here, now we can find out roots, and if you plot that, what you can see that we have poles on right half of the plane, so system will be unstable. If we find out its response, we can see its magnitude is increasing with respect to time, and at t goes to infinity, it can go to infinity. So the system is unstable. So this is how we can find out. Now if it is only for first order, second order, third order, it is very easy to find out the roots of the characteristic equation or the pole values. We can find out easily. But if it is a fourth order system or more than that, okay, sixth order system or more than that, then it is very difficult to find out the roots by pen paper calculation. Okay, we have to use computer for that. But there is another method that we can apply so that we can solve in using pen and paper higher order system very easily. Okay, that method is known as Routh Hurwitz stability criterion. Okay, this is a direct approach in order to determine the stability of the system. Okay, when in this analysis, characteristic equations are mostly large and complex. Then we can apply this Routh-Hurwitz unity criterion. Hence, it is difficult to simplify them into roots if it is order is 4 and above. Now, for such situations, Routh-Hurwitz method provides an easy and quick method to determine the stability without the need to disintegrate the characteristic equation. That means without calculating the value of poles or the roots of the characteristic equation, we can find out stability of the system. Okay, using this Routh-Hurwitz stability criterion. Now this is introduced by Edward John Routh in the year 1876. Okay, and in this particular method we have to form one table that is called Routh table. Now Routh stability criterion allows the determination of whether there are any roots of the characteristic equation with positive real part. Okay, if there are, then how many number of these roots are there. Okay, that we can find out without actually finding the roots. That means using Routh stability criteria we can find out how many roots are there, okay, in the right half of the plane, and the number of roots, whether we have one root, two roots, three roots in the right half plane, that we can find out without finding the actual value of the root. Okay. Now Routh-Hurwitz criterion states that the number of roots of the characteristic equation with positive real parts, that means lie on the right half of the plane, is equal to the number of changes in sign of the first column of the Routh array. Okay. First, let us construct the Routh table. Then we can understand this concept very easily. Now, first step is checking the stability of a system using Routh stability criterion is the application of initial test called Hurwitz test. What is that meaning of Hurwitz test? The necessary but not sufficient condition for a characteristic equation to have all its root with negative real parts is that all of the coefficient must exist and have the same sign. This is the Hurwitz test. If the characteristic equation fails to meet the above condition, the system is not stable. That means we must have all the coefficient of S value. If there is a missing term, that means system is unstable. Okay, that is a condition, but that is not a sufficient condition. If, however, the condition is satisfied, then no conclusion on the stability of the system can be reached. For that, we have to apply Routh stability criterion. Okay. Now, to apply Routh stability criterion, Routh array or Routh table must be constructed. Okay, and that we have to construct it from the characteristic equation or the denominator polynomial. This is the example of, this is the form of denominator polynomial. Okay, that is an, this is the coefficient, a are the values of coefficient. Okay, s to the power n. Okay, now what we can write, we have to write the coefficient in two rows. Okay, first row start with a to the power a n, second row starts with a n minus 1. Other coefficient alternate between two rows. Okay, both rows should be the same length. Okay, then we have to continue until no coefficient are left. Otherwise we have to add 0 as the last coefficient if necessary. So this is how we can construct two rows. Let me show you that how we can put the values. Say for example, this is your denominator polynomial. Okay, what we have, fourth order system, s to the power 4. So a4, so we have to start, we have to take a column where you have to put from this maximum value of s to minimum value. Okay, s4 to s0. Now first two row we have to put all the coefficient value into that row. We have to start from first value, s to the power 4 coefficient a4. Okay, then next coefficient s to the power 3, that we have to put in second row. Then next coefficient, that is of s square term, that comes in first row. Next coefficient comes in second row. Next coefficient goes into first row. This is, there is no other coefficient, we have to put it 0. That means what, these coefficient values from the highest power we have to put in alternate row, first row, second row, again first row, second row, first row, second row, like that way. Okay, then we have to compute the other values of coefficient. Okay. Now how to compute the third row? Say how to compute the third row. For that we have to find out. Okay, let me discard these lines and let me show you once again. So how to compute this third row after inserting all the coefficient in first two rows? What you have to do? You have to find out with respect to first column. We have to do the calculation. Okay. So that what you have to do? A3 minus A2 minus A1 minus A4 divided by A3. Okay. Similar, or we can write determinant of these four factor A4, A3, A2, O1. We have to find out by A3, then multiplied by minus. Determinant means A4 minus A1 minus A3 minus A2. If you multiply that with minus, that will become A3 minus A2 minus A4 minus A1. That I am telling you previously. A3 minus A2 minus A4 minus A1 divided by A3. That will be your first value. Second value will be what? With respect to first column, we have to take. Okay, that is A4, A3. Then next column value you have to take. So A3 into A0, A4 into 0 divided by A3. The first column, I mean, in first column, the last row, okay, we have to take as a division value. So A3 is the common factor. Okay, so we are getting this B2 and we don't have any value here. So that will be 0. Okay. This is how we have to find out the third row. Now this is the way we have to follow for next row. So this is your now we have to find out this row, say value of this row. What you have to take? We have to take the previous two row. Okay. Then you have to apply that. So B1 into A1 minus A3 into B2 divided by B1. Then B1 into 0 minus A3 into 0 divided by B1, like that way. Now if you have to compute this row, we have to consider the previous two row value. Okay, that then what will happen? C1 into B2, B1 minus 0 divided by C1. Okay, that will be your D1. So this is how we have to find out all coefficient values. So let us take one example of that. So this is your characteristic equation. Okay, so starting value s cube. So we can start from s cube up to s0. Okay. So what is the order of the system? If this is n, how many rows should be there? That should be n plus 1. Okay. Because we have s to the power 0 down. Okay. Now we have to put all the coefficient value alternately. So 1, then that should be 10, 31, then 1030. These values are 0. Alternately you have to place. Then you have to calculate. So 10, 1030 we can divide by 10 this row. So 103. So what we can do? 1 into 31, 1 into 103 divided by 1. Okay. 1 into 31, 1 into 31 minus 1 into 103. So it will be minus 72. Okay. Then this will be 0. Okay. Now we got this value. Now we have to find out next row. That will be taking last two row. Okay. So when whichever row you have to calculate, we have to take before before two rows. Okay, just before two rows. So 72 into 103, 1 into 0 divided by minus 72, that will be 103. Okay, so that will be the route table. Okay, now from that what you have to do? How we can find out the stability criterion? Stability criterion states that number of sign changes in the first column. The first column is the main factor. Okay. If in the first column there are sign changes, number of sign changes of the route in the first column of the route table equals the number of roots of the polynomial in the closed right half plane. That means it the poles are present in the right half plane of S plane. Okay. So we have to look for sign change in the first column. Now you can see plus 1, minus 71, 72. So plus to minus, so there is one sign change, right? So one sign change. Now from minus to plus, so there is another sign change. So we have two sign changes. That means the system is unstable and two poles are there on right half plane. So one pole should be there on left half plane, because this is third order system. We must have three poles. So the system is unstable. Okay, this is the way we can find out. Now let us take another example of that. Okay, so this is your characteristic equation. So starting from S5 then up to S0, S5, S4, this is the first two row where we have to put all the coefficient value alternately. 1, then 2, then 4, 3, 4, 2. Fourth column is 0, 0. Now we have to find out next value. So we have to consider previous two rows. So 2 into 4 minus 1 into 3 divided by 2. It will be 8 minus 3, 2.5. Then 2 into 4 minus 2 divided by 2. Okay, that will be 3. Other part are 0. Okay, then we have to find out next row. That is, we have to consider previous two rows. 2.5 into 3 minus 3 into 6 divided by 2.5. That will be 0.6. Okay, you can do the calculation. And 2.5 into 2 minus 2 into 0, okay, divided by 2.5, that will be 2 itself. Okay, now we can find out next value taking previous two rows. Okay, so zero point 0.6 into 3 minus 2 into 2.5 divided by 0.6, this is the value. Okay, and here it will be 0, so it's 0. Next value, this into 2 divided by 0.6 into 0 divided by minus 0.533, so it will be 2. Okay, now what we can see, let me discuss that part. Now what we can observe, that we have to look into this first column. Okay, we have to look into this first column and we have to observe that we have any sign change or not. Now we can see that it is plus sign, here it is minus. So we have one sign change here and minus here plus another sign change here. Okay, so we have two sign changes. So number of sign changes 2. So two number of poles lie on right half plane of S plane. Then we can say system is unstable. Then the question is how many poles are there on left half plane? That will be 3, because order is 5. So 5 poles should be there, or 5 roots. 2 lie on right half plane, so 3 should lie on left half plane. Okay, as we have two poles lie on right half plane, system is unstable. So this is one of the example. Similarly, I have taken another example that we can calculate. Okay, so here S equal to 6. So first row, second row, we can put the values alternately: 1, 2, 6, 5, 7, 2, 3, then 0. Okay, then we can calculate 6 into 12, 2 into 6 minus 5 divided by 2, this is the value. 2 in 1 in 2 into 7, 1 into minus 1 into 2 divided by 2, that is the value 6 here. Okay, then 2 into 3 minus 1 into 0 divided by 2, it will be 3. Next we can find out next value taking previous two row into consideration. Okay, so 3.5 into 5 minus 6 into 12 divided by 3.5, this is the value. Okay, similarly 3.5 into 2 minus 2 into 3 divided by 3.5, we get next value. So like that way we can solve to get all the coefficient value. Then we can see there is a plus 2 minus 1 sign change, minus 2 plus second sign change. So we have two poles on right half plane. Then how many poles are on left half plane? The four number of poles on left half plane, because this maximum power is 6. 6 poles should be there. 2 on left right half plane, so 6 poles should be on left half plane. As 2 poles on right half plane, system is unstable. Okay. Now let us solve a very one method, that is how we can find out condition. Okay. Say let us check for uh, quadratic, I mean second order system where we have a quadratic equation. Second order system s to the power 2. Okay, so this is the formula to find out pole. And what we can do, we can a square plus bs plus c equal to 0 is the characteristic equation. So we have a square plus s and s to the power 0. We can put the coefficient value 1b c 0, other terms as 0. Now we can find out b into c minus 0 divided by b, that will be c. Now we have to look for first column. So what is the condition for stability of the system? The condition is your b value must be greater than 0. B value must be greater than 0, right? Then only it will be positive value. If it is less than 0, it will be negative. Then system will be unstable because there will be a sign change. And C value should be greater than 0 also. Okay. Then what happens? If B, C both are greater than 0, then system is stable. Okay. So both coefficient should be positive. Now suppose if we have C positive is negative, what will happen? There is only one sign change, right? Plus to minus. That means one pole on right half plane of the S plane, system becomes unstable. Okay. If we have B also negative, then plus to minus, minus to minus. So one sign change, system is unstable. Okay. So condition is BC coefficient must be positive for a quadratic second order system. Okay. If for third order system, what will happen? We have term S cube third order system, and here it is s to the power 0. So we can put all these coefficient value alternately 1a b c. Now we can calculate, that is ab minus ac divided by a. So that if you divide a by both sides, then what you will get, b minus, okay, not ac, this is only c. Okay, this is only c. So that will be b minus c by a. That is the condition here. Okay, it will be 0. Now if for to find out this value, this one into c minus 0, okay, divided by this factor, it will be c. So now we have to look into this first column and we have to find out condition. What is the first condition? For this, a must be greater than 0, c must be greater than 0, and from here this b minus c minus b minus c by a, that must be greater than 0. So what we can write, b must be greater than c by a. Okay, then only your third order system will be stable. So b should be greater than c by a. That means whatever the value here b, okay, that must be greater than c by a, then only system will be stable. So this is how we can find out condition for any system, find out condition for stability. For second order, third order, I have taken these two examples. Okay. Now let us solve one question. Okay, first example, and this is your GS. Okay, and this is a stable transfer function. You can see we have all the poles on left half plane s equal to minus 2, minus 3, minus 5. Okay. Now we have included one controller variable 1000. Okay. Instead of having this one, we are inserting a controller gain factor as 10,000. Okay. So this closed loop transfer function, if you want to find out closed loop transfer function of this system, that will be this value using the formula g divided by 1 plus gh. Here h equal to 1. Okay. So g divided by 1 plus this factor. So you can multiply and you can find out that it will be 30 plus with. So this is the factor. Now what happens? Now what happens? This is the value 110 31 1030. So 110 31 1030. If you solve it, then if you look into this particular column, what we can see, that two poles on right half plane, because we have two sign change, plus to minus, minus to plus. So what we are getting? We are getting that we are destabilizing the system. It is a stable system, but if we insert one gain of 1000 and give a negative feedback, system becomes unstable. But it doesn't mean that feedback is destabilizing. What happens because of this third order factor? Okay, condition is B should be greater than C by A. Okay, so this factor give makes your system unstable. Okay. Why? Because this 1000, this proportional constant, this constant value is much higher. If you reduce that value, then we can get your system stable. Okay. That is the point. Now let us solve another problem that finds the stability of a system with characteristic equation given as this. So here we can see this is third order system. So your A, B, C all are greater than 0, fine, and B is greater than C by A, right? 8 by 6 greater than whatever the value, B is more than that. So system must be stable. Let us prove that. So S cube, S square, okay? We have to put all the coefficient value alternately 1, then 6, 12, then 8. Now we can find out S1, S0 factor. It is 6 into 12 minus 8 divided by 6. 64 by 6. Then this is 0, okay? Now this one into 8 minus this 0 divided by this factor, so it will be 8. Now we can see from this first column there is no sign change, so what we can say, system is stable. Okay, all the roots are on left half of the stem. Okay, now say another problem. What we can see here, this is a third order system. What we have done, A, B, C all greater than 0, but this B value should be greater than C by A. Now this is less than that, so system must be unstable. That we can check using this Routh stability criteria. That is S cube, S square, first two row we have to put all the coefficient value 1, 1, 2, 24. If we multiply these two factor, 2 minus 24 by 1 minus 22. Now minus 22 into 24 minus 0 divided by minus 22 is 24. Now what we can see here, we can see plus 2 minus 1 sign change, minus 2 plus second sign change. So two sign changes are there. Okay, so two poles lie on right half plane. Okay, and one pole lie on left half plane. Okay, so as two pole lie on right half plane, system becomes unstable. But we can say, we can find out the condition from the condition itself that we have solved for the third order system. Okay, now let us, this is another type of problem, that is determine the range of values of a system parameter k. Okay, we have a system parameter k, we have to find out its range for which the system is stable. For that we can form the Routh table. So S cube is the factor, S square, alternately you have to write the coefficient 1, 3, 3, and this is your altogether constant. Instead of having one simple constant C, we have a with k term. Now we can vary k so that your system will be stable. Okay, that is the controller. What is the use of controller, that I will cover later. Okay, now we can calculate, that is 3 into 3, 9 minus 1 minus k, so 8 minus k by 3. Okay, this factor is 0. Now this one into 1 plus k minus 0 divided by this factor, so it will be 1 plus k. Now we have to find out the condition. So this column, for stability, this column must be positive. All values should be positive. There should not be any sign change. Okay, so what we can say, that 1 plus k must be greater than 0, right? Then only it will be positive. And this factor 8 minus k by 3 should be also greater than 0. That means what we can write, 8 minus k should be greater than 0. Okay. So from this, what we can say, k must, from this factor what we can say, k must be greater than minus 1, and from this factor what we can say, k must be less than 8, right? If we put k less than 8, okay, 7, then it will be positive value. If we put here k greater than minus 1, okay, then it will be positive value. So the range of k lies between k greater than minus 1 and k less than 8. That is the condition. Then your system will be stable of this particular characteristic equation of a particular system. Okay. Now we can solve another problem. Okay. We have to find the stability of this one. This is a fourth order system, so we didn't derive any condition for that. So let us find out directly using this Routh table. Okay, so Routh table is this one. So alternately you have to put the values of coefficient 2, 1, 3, 5, 10. This one should be 0 because we don't have any other coefficient. Now we can calculate 1 into 3 minus 5 into 2 divided by 1. This is minus 7. Okay. Now 1 into 10 minus 2 into 0 divided by 1, that will be 10. Okay. Now we have to find out next row value taking previous two row into consideration. So minus 7 into 5 minus 10 divided by minus 7, we have this value. Okay. And this is 0, so it is 0 now. Now this one into 10 minus 0 divided by 6.43, that will be 10. Now we have to look into this first column. What we can find out that from here to here we have a sign change, plus to minus, again minus to plus, second sign change. Okay. System becomes unstable because we have two sign changes in the first column of Routh table. That means two roots are there on left half of S plane. Then we can find that two poles or two roots are there on left half of S plane, because here order is 4. 4 poles should be there. So we can say two poles on right half plane, two poles on left half plane. Okay, that means system is unstable because of poles on right half plane. Okay, so this is all about this Routh stability criterion, how to uh, construct the Routh table. Okay, then what is the condition for stability and what we can find out. Now there are some point, okay, in this Routh stability criterion topic, that what will happen is, mm, what may happen is that in one particular column, okay, what, suppose we have a particular, let me discuss this. What we can have is that in Routh, during construction of Routh table, we have some value here. Say in first two we have some values. Okay, what may happen that in one row, okay, first column value becomes 0 and we have some other column value. Okay, one first column value of a row becomes 0. Okay, it can happen. How? Because say this is 1 1, this is 1 1, so 1 minus 1, 1 into 1 minus 1 minus 1 by 1, it will be 0. If this happens and other row values becomes uh, non-zero, then we cannot solve it directly. So we have to do some process to solve it and find out stability. Okay, and how many poles are there on right half plane. This is the first case that we have to look into, and we can have another case, that is in first two row we have some values. Okay, and what happened, one of the row, entire row can become 0. Okay, here one element, first row element becomes 0 in one row, other elements are non-zero. That is the case 1. Case 2 is entire row becomes 0. Then what will happen? Okay, case 2. So in next lecture I will discuss about these two point in for these two cases, and how we can solve it and what conclusion we can make. Okay, so thank you so much. uh, so you can go through this particular video and you can find out the concept of Routh criteria properly, and after that you can look for the next video so that you can find out for this case 1 and case 2 how to solve the problem. Okay. Thank you so much.